Okay, we got Zoom going and recording. I'm going to share the screen. Good morning, everybody at home or on campus, but not in the classroom. Okay. What's that? On my laptop. Well, it's a good way to like type questions and stuff, and you can see this. I guess you can see the screen pretty well. You don't have to. If you're in the classroom, you don't have to be on the Zoom. But if you want to be, you can. Okay, let me start our attendance. And I know I had Cloud going, but maybe I didn't sign into Cloud. No, I didn't sign into Cloud. Let's sign into 6 different things before class starts. Okay. And we're going to do a question. Oh, gonna make it big. Move this. Let's go away. Okay, so y'all can do attendance whenever you can. I want to see if my pen works today. Me and the smartboard were not getting along yesterday in another room. So I wanted to make sure I didn't have bad luck again today. We still got about 3 minutes. Okay, let's see. So I'll tell y'all a joke. Y'all want some good cheesy jokes? So I put a joke in my son's lunchbox every day. I don't put a joke in his lunchbox. I'm in trouble. So this was today's joke. What kind of an animal do you want? Wait. See, I'm bad at jokes. That's why I write them down. What kind of animal do you want to take to battle with you? An armadillo. Thank you. I love the sound effects. It just makes it. Let's see, what do you do? Here's another one. What do you do if your dog takes your English homework? You take the words right out of his mouth. It's hard to find enough jokes to put one every day that he can get. He's 8. So like half the time I'm like, oh, that's a funny joke, but he's not going to get it. So yeah, it's a struggle. But he seems to enjoy it, so I don't feel too bad.
Yeah, that's the good thing about kids. They're also fairly easy.
Fairly easy to please, but he will tell me, Mom, make me laugh. And I'm like, dude, I give you a joke every day. Is that not enough for you? Apparently not. But half the time I tell him a joke, he doesn't laugh. Oh, did I tell y'all this one? This is one of my favorites. He heard this on a PBS TV show. But what is a tree's least favorite month? September.
Oh, that's a good one.
It's really funny when he does it. I should record him doing it. He does it much better delivery than I do.
So I'll take your word for it. I'll take your word for it.
All right. Got about 2 more minutes. If anybody else wants to contribute. I think I'm out.
Not me. I didn't get that. So, like, 7th grader.
Yeah, he saw it on Nature Cat. He likes to watch Nature Cat.
I don't watch that.
Yeah.
I could tell from the Joe that was that show.
Yeah, can't you? He loves Nature Cat. Oh my God, he loves Nature Cat.
Yes.
Boy, we're a little light in the classroom today, huh? It's pretty empty over here. And remember, tomorrow, Friday, Friday, even though it's virtual, if you feel like coming in the classroom, this is where I project from. So
Some that like you have to come into come in for lab on Friday. Like,
then you don't have to.
no, it's like what are we supposed to do for both the class for best nine on lab, 9 lab? What are we supposed to do?
You're gonna have a Labster. We finally got Labster, I think, almost figured out.
Is that
So it's an online.
Is that website I have to download?
It's not a website you have to download. You access it from the internet. How y'all doing?
Good. So I actually have a lab after this class, but Caitlin's just gonna stay and she's gonna come at home.
Makes sense. I get it. Probably makes sense.
Yeah, that's fine. Okay, I think we're all about here, so I think we're gonna get started. So if you have not responded to attendance, please go ahead and respond to attendance. Okay.
Are we supposed to? I thought. Wait, break. I thought the semester was going to be over before Thanksgiving.
It is. It is. It should be. It should be. The question was, should this semester end before Thanksgiving? Yes, it should. That's the plan. I don't know how well the plan is going, but we will see.
Did they figure out how they were gonna make up some days?
I would love to know that. I would love to know how we're gonna make up this day.
Monday was saying they were gonna try to make us come on Saturday.
Yeah, that's the one.
And I'm like, no. No.
Yeah, how about no?
I don't know. I really wish I knew, and I really wish I could give y'all information, but
Okay.
I do not. Okay, so we're gonna pick up. We're gonna pick up on some clicker questions. What should you have watched? Oh, I got a question. Hope to have. Oh yeah. Fingers crossed that we're all done before Thanksgiving. Fingers, legs, arms, like everything. So what should you have watched before you walked in the door today?
Watch 3.2, chapter 3,
Chapter 3, section 2. We only have one more chapter after this, and it's like, I don't know what it is with them, but the last section of the chapters tend to be smaller. So it's kind of like a lot of work on the front end, but then at least you have the weekend, and then it kind of drops off content-wise, right? So by the time you walk in tomorrow, Friday, if I could get my days straight, you should be done watching all the lecture videos. Section 2.
We still have our Labor Day. We still have Labor Day.
Theoretically, we still have Labor Day. I haven't heard any differently. I haven't heard anything officially about how things are going to
I think they
change.
should just call it a lost cause. We just lost it.
You're welcome to send those views to the Student Government Association to see if we can, figure something out. But yeah, so Dr. Westbrook needs to talk to SGA. There we go. We still have Labor Day. Okay, so Ethan knows we still have Labor Day. Yay! Yeah, I don't think we're gonna have a fall break. I don't think so. I highly doubt it. That's only 2.
No fall break, and they're trying to get some other days.
Yeah.
He said no fault.
No fall break. That's what. Yeah, that's pretty.
Oh, fall.
Okay. Everybody checked in? Everybody checked in? Because I'm looking at 55 responses. And I know we have 60-something people in the class. I'm hoping everybody's participating. My clicker is still stuck. No, you're still stuck on class attendance. That's right, because I'm still letting people do their attendance. So Sadie, you're okay. You're okay, because we have a few people who just walked in, so I'm giving them a second to get checked in. Okay, I think we're all about ready. Okay, so we're going to change. We already talked about topoisomerases, right? And how that can affect cancer. And then I went off on the cancer talk for 5 minutes last class period, right? Okay, so now, what kind of nucleic acid are you most likely looking at? Be thinking about why. Be thinking about why. I'm trying to get my chat. Oh, I'm going to try to join the meeting on here and view my chat on my laptop. This is my goal. Yeah, but like I want it to stay awake, so my phone's gonna keep going to sleep. I'm hoping that I can do this. Okay, so 50, I thought we were at 57. We need one more person, but I'm gonna call it at a minute. Let's see if I could join as myself. How many times can you join one Zoom session, right? Okay, so what you should have said is that this is, mute myself. Okay, that this is RNA. Why is this RNA?
Because the uracil present.
That's one thing, uracil's present. Now, what if I gave you a structure like this, and I didn't tell you what the bases were? Could you tell me if this is DNA or RNA? You could say this is most likely, like it's not that it's impossible, but it doesn't usually happen, that this is most likely RNA, just from the shape. Why? We know that RNA contains uracil. What does uracil do to the RNA molecule? Like, what's the point? So it doesn't have an OH in the DNA form, and it has an OH in the RNA form. What's the point? How does that create a different function? Y'all know there's going to be discussion on the exam, right?
Yes, we know. Yes, we know. We can't.
So the uracil is less stable, right? Because you can have nucleophilic attack, right? And it can break the backbone. That's right. Okay, so RNA is less stable. Do we want RNA to be less stable? Yeah, we actually do. We actually do. It's actually a really good thing, right? Because you want RNA to degrade pretty quickly. Because what happens if the cell is in a dangerous condition, a bad condition? You want to change transcription of certain genes and upregulate certain things and downregulate certain things, right? And we do that by making more RNA of something or making less RNA of something. Well, if you then take that cell and put it into great conditions, you want those levels to change, the protein levels to change. How do we do that? By changing the levels of RNA. So what happens if the RNA sticks around? Our cell is still expressing proteins that are like, oh my God, I'm in this bad condition, this bad situation, right? So if the RNA turns over very rapidly, that's what we want. But tell me how this three-dimensional shape affects RNA function. Should have read it and heard it in the lecture a little bit.
Can DNA form the hairpins too?
They can, but it doesn't happen as frequently. This is very common in RNA and very uncommon in DNA. So why is this common in RNA?
Because of uracil. DNA.
No, not quite. But like, why would you want RNA to make these crazy structures? Whereas DNA only makes a double helix. To help stabilize it, that's exactly right. To help stabilize it.
No, I bet you said the whole point of the RNA was that it make it less stable, and so it's
Right.
gradient.
Think about, is every single RNA molecule in the cell going to do the same job?
No.
What kind of RNA do you have?
So wait, is it supposed to be stable or supposed to be unstable?
Well, that's a good question. We're going to answer it right now. What kind of RNA do you have in the cell? mRNA, tRNA, microRNA, right? Do you think they all have the same function? No. So do you think they're going to have different structures? Yes. tRNA, do we want to keep it around? Yeah, kind of. So it has all kinds of interesting three-dimensional configurations. How about mRNA? Do we want to keep mRNA around for a long time? No, no. We want mRNA levels to be able to change very quickly. That's what turns into proteins. So we want to be able to change that very rapidly, right? You want to get it from the nucleus out to be transcribed and be done. You don't want it to hang around, right? So what do you think is going to have more three-dimensional configurations, mRNA or tRNA? tRNA. Does that make sense? Oh, small nuclear, yes. And you also have snRNA, small nuclear RNA, yes. Okay, so now we're gonna look at our structure here and tell me what is the secondary structure that's found at position 1. There are all kinds of different secondary structures. And part of the lecture, I talked about the different kinds of secondary structures. So which one are we looking at in position number 1? So right here. And be thinking, can you identify all of them? I'm calling it at 1 minute, so you have about 5 seconds. Okay, so what did we say? So this one should be a bulge. This one should be a bulge. How do I know it's a bulge? There's not another unpaired over here. So this uracil is in a bulge. This uracil is a bulge, right?
So it's a bulge because there's a pair of uracil, because there are pairs of uracil that have been partnered.
It's not necessarily that there's a pair. It could only be one. But on the other side, there's no match for this uracil, right? There's nothing for that uracil to interact with. So that's the bulge. So this is one bulge. This is a second bulge. Okay, what are the rest? What's this one? This is a hairpin. How do you know it's a hairpin? First, you have to see that you have double-stranded, right? It's double-stranded, and then the double-stranded ends in a loop, right? Okay, so we got a hairpin. How about this one? This is a duplex, right? Now, here's an interesting one. What's the difference between a loop and a hairpin? It doesn't start with a duplex. In a hairpin, you have duplex, loop. In a loop, you actually have duplex on either side, right? But it doesn't lead. You don't have a duplex leading into a loop. That's the difference between a loop and a hairpin. That's what I see most people get confused on, right? Okay? All right, now we're going to talk about, now we're in section 3.2. Okay, let me move this down a little bit. All right, which of the following best describes monocistronic and polycistronic? Okay, I'll give y'all until 1:30. Okay, so what did we say? Ooh, we're split. We're split between A and C. All right, so it is C. So what's the difference between A and C?
For A, saying that monocistronic is like for the A, for A, it's reversed.
It's reversed. So A and C are reverse of one another. Polycistronic. Whenever you hear poly, you want to think multiple, right? But the question is multiple what? It's multiple genes under one promoter. So what kind of organism do you think would need multiple genes under one promoter? And why? I'm always going to put that on an exam. You know that, right? And why? Okay. What? Yes, it would be a prokaryote. Why would it be a prokaryote? It's exactly right. It's a space thing. Do we have a lot of DNA? We have a lot of DNA, a lot. So we have tons of introns, we have tons of space. But in a prokaryotic organism, you have a limited number of base pairs inside of that genome. So you're going to make the best of the small stretch of DNA that you have. So how do you do that? You put genes that are in the same biochemical pathway under the same promoter, right? If you are undergoing starvation, right, you have a bacteria that's got no food, you're going to want to turn on a certain set of genes, right? And so you put all of those genes that are in the same biochemical pathway of energy conservation under the same promoter. And at the same time, in conditions of lots of food, you're going to want to downregulate those starvation genes and upregulate the ones that say, ooh, we've got food to eat, right? We can do things. So you put those under the same promoter. So there's a reason why. Okay. And so when you do this, you have, right, one DNA transcript. It gets turned into how many mRNA molecules? If you're polycistronic, one mRNA molecule, from one mRNA molecule into multiple proteins, right? That's where the poly comes from. We're going from one stretch of DNA into multiple genes. But make sure you know where that change occurs, right?
So it goes the polystronic, you go polystronic, then the mRNA, and all that, then it becomes the sequel, then it becomes the proteins.
The multiple proteins, that is correct. Yes, yes, yes. And so if you have something that's monocistronic, right? One promoter, one DNA, one mRNA, one protein, one everywhere, right? Okay. All right, so here we go. Here's our example, right? Our eukaryotic genes